Good morning, good afternoon, good evening, mammals. Got another in case you missed it video here from material that we covered right before we left for our NTI break. So something that you can go back to and refer to if you need it. This video is on the ionization energy trend. So when we did this in class, before we even defined it, we looked at what happened to ionization energy as you go to the right and what happens as you go down. So you can look at these numbers. There are a few exceptions, like here, when you switch from D to P blocks, and here as you go down, because in the sixth row for the first time you get the F block, but the exceptions aren't super important. I'm not going to ask you any questions where I want you to consider the exceptions other than to know that they're present and not be freaked out if you see a data set and the data isn't perfectly consistent. But the overall trend you can see on most of these rows is as you go to the right, ionization energy increases. So we increase as we go to the right. And you can see that as we go down, ionization energy decreases. So ionization energy generally increases as we go up. So that means, just like effective nuclear charge, the highest element in terms of effective nuclear charge and ionization energy is helium, and the lowest is francium. Again, this is true for effective nuclear charge and ionization energy. And I'll define that ionization energy for you right now, and we'll link it to why when effective nuclear charge is high, ionization energy is also high. So what I've got here, ionization energy is the energy to remove an electron, making a cation. So this is how difficult it is to come in and pull an electron away from an atom, making it high, or making it positively charged. So elements over here on the metallic side of the table tend to have very low ionization energies, and elements over on the non-metallic side tend to have rather high ionization energies. And the way to think about why that is the case is that if elements have a high effective nuclear charge, that means they have a high attraction for their own electrons. And that's going to make it more difficult to remove an electron. So when the attraction is high, the energy to remove the electron is also high. And another way of thinking about that is thinking about how they choose to bond. Elements on this side of the periodic table, their best option for bonding is to lose an electron and become like the noble gas. So it's kind of a good day for these elements over here if they lose an electron, because then they reach their noble gas state. And so that's why the energies to do it simply aren't very high. And on the flip side, elements over here, they would rather gain an electron to reach their noble gas state. So taking an electron away from them is moving in the opposite direction of their tendencies. So the ionization energy for those elements is particularly high. We also looked at not just the ionization energy for the first electron, but for multiple ionization energies. And multiple ionization energies are the energies to remove additional electrons. So we had this chart here of the energy to remove the first, second, third, fourth, and fifth. And what I want you to note is that it always increases. The second electron is always more difficult to remove than the first, and the third is always more difficult to remove than the third. And we looked at a pattern here using some of our elements that might become cations. And what we noticed is the increase, where they have a large increase, makes this kind of stair-step pattern on this chart. So I'm circling between the ionization energies where there's the largest increase in ionization energy. So what we can see is lithium loses its first electron quite easily, but then there's a large cost to removing the second. Beryllium loses its first two rather easily, and then there's a high increase to remove the third, and so on. And we linked this pattern to their valence electrons. So what we said is that the large increase in ionization energy occurs after the valence electrons have been removed. And the reason that is once you remove the valence electrons, you're now removing electrons from inner shells. These are going to be closer to the nucleus, so they feel a greater attraction, a greater effective nuclear charge, which makes them more difficult to remove. Okay, so I've drawn out an example here to try and illustrate that. I've drawn sodium. So if we remove sodium's first electron, this electron right here, it sees an attraction from 11 protons, and it feels repulsion from 10 inner electrons. And so it's going to be removed based on this effective nuclear charge. And once we remove this guy, once he's gone, we're going to be removing one of these next inner electrons. And this second inner electron, it still sees an attraction from 11 protons. But since it's closer to the nucleus, it only feels repulsion from 2 inner electrons. And so it has a greater effective nuclear charge because we're getting the same amount of attractive forces to the nucleus with less repulsion. And so that means it's going to be a much more difficult electron to remove. So in summary, what we're looking for on the periodic table is that effective nuclear charge increases as we go to the right and increases as we go up. So if you're asked to rank elements based on their effective nuclear charge, their ionization energy, it's the same pattern for effective nuclear charge. The closer they are to helium, the higher their effective nuclear charge, and the higher their ionization energy. And the closer they are to francium, the lower their effective nuclear charge, and the lower their ionization energy. If you're asked a question about additional ionization energies, what you're going to be looking for is you're going to be looking for the place where the ionization energy makes a particularly large jump. And so that jump is going to happen after you've removed the valence electrons. So if you can find the largest jump, you know that all of the electrons before that large increase were valence. So this particular example would have 2 valence. So it might be magnesium and it might be calcium. And then everything after the large jump are going to be inner electrons. So you can identify the element that way. So I hope this helps. In case you come across any questions on the review material or quizzes or tests asking about ionization energy, you can come back and refer to this. And as always, look out for yourself and others, practice good hygiene, and I'll see you on the flip side.